Hi, I'm Matt Needham. This is my lecture on condensers. There's really two types of main condensers. The air-cooled condenser, which you're probably very familiar with by now, that runs window units in your car AC and package units, split systems, a lot of small refrigeration type systems. And then there's also water-cooled condensers, which are generally for larger systems. And we're going to go over both. Let's start with air-cooled condensers and just do a quick review of the refrigeration cycle with an emphasis on condensers. And also we're going to go through it a little bit with the thermostatic expansion valve. We've been over it with the capillary tube type before, but let's do this with an emphasis for the condenser. So remember, as the refrigerant travels into the evaporator, it's a low temperature, low pressure liquid with a little bit, poquito vapor, and as it travels through the evaporator, it absorbs the heat from whatever we're trying to cool down, like your room or whatever, or zone. And then the compressor sucks this from the largest suction line and gives it an honorable discharge out the discharge line. That's hot. Woo! Okay, and as it travels down the discharge line, it desuperheats, and then it comes to our condenser, where we're going to dump the heat into a place we don't care. If it's a window unit or central AC system, we generally dump it outside. If it's the refrigerator in your home, we actually dump it into the kitchen. And as it travels here, it desuperheats, and then it starts turning in the middle of the condenser from a vapor into a liquid. And because air, the reason it's called air-cooled condenser, is you always have air passing over, generally with a fan, blowing air directly over the condenser, which is how it cools off. And then you become 100% liquid here near the end of the condenser. In the last little bit of the condenser, you get subcooling, which is the number of degrees below the saturation point or the number of degrees below the condensation point. And then you travel down this little bit smaller line, the liquid line, and we come to the thermostatic expansion valve, which is a type of metering device, and it has a sensing bulb here with refrigerant in it, and actually the refrigerant that's here has nothing to do with the refrigerant here. In fact, this sensing bulb does have refrigerant in it, even though we can see there's no refrigerant inside the central part of the valve. And as the suction line warms up, it creates more of an opening force, letting more refrigerant flow through, more liquid refrigerant, which allows it to, it then boils off later because you let more liquid refrigerant go through, and the superheat would go down. How this functions is it's three forces that act upon the expansion valve. The opening force, which is sensing bulb pressure, opposed by the low side pressure on the other side of the diaphragm plus spring tension, and there's this balancing act all the time that causes it to open and close to regulate superheat, which might be around 8 or 10 degrees at the outlet of the evaporator. Okay, so that's just a little overview, and then you see some of these tubes that are coming from the expansion valve outlet to the evaporator. That little pipe, those little tubes, is called the distributor because it distributes the refrigerant evenly to the evaporator and cuts down on unregulated pressure drop. Okay, so our air-cooled condenser, very common. And let's talk about the head pressure. And sometimes we have to regulate the head pressure because we're running systems when it's kind of cooler outside. And if your condenser's outside and you're blowing air over it, especially in refrigeration, you need to run the system even when it's 20, 30, 40 degrees outside. You still need refrigeration for your walk-in coolers and freezers, etc. And so a lot of times the somewhat larger commercial systems can have 2 fans, not just 1, or even on air-cooled chillers up to 12 fans. So all 12 fans wouldn't be running unless it was a very hot day, and the head pressure goes up with the temperature of the air going into your condenser. And then a pressure switch will bring on more and more condenser fans. So we control head pressure a lot of times with a pressure switch, which brings on more and more fans. The other ways that we can control head pressure with an air-cooled condenser is like a variable frequency drive fan that speeds up or slows down with head pressure. Also, sometimes we'll have a certain type of bypass valve. It bypasses the condenser or a portion of the condenser, the refrigerant where we're going around the condenser. That maintains a head pressure when the condenser is in a very cool environment. So we do have to have head pressure control when we're running systems, especially when it's not very warm outside. Also, again, with that, what head pressures are acceptable? So you should never really see a head pressure greater than 30 degrees above the ambient. Now, what do I mean by that? Well, if it's 70 degrees outside and you add 30, you get 100 degrees Fahrenheit. You can then look on a pressure temperature chart at 100 degrees, go across and find the pressure, and your head pressure should never be above that. Now, with modern systems like R410A, a lot of times the head pressure actually runs more like 15 or 20 degrees above the outside air temperature, where you would take the 70 and look at 85 or 90, and that's actually what your head pressure should be at. But we should never have a head pressure greater than 30 degrees above the ambient temperature. Now, ambient isn't always outside air temperature. Like, obviously, the air going into your condenser in your refrigerator at home is the temperature of your kitchen. So that would be the ambient for the condenser for your refrigerator. So you take 30, you add that, and that would be the maximum head pressure that you'd ever want to see on really any type of system, and this works for just about any refrigerant. And that also leads us to something that I've kind of come up with. You won't really find it in the book, in where we can set our head pressure cutouts or test the head pressure cutouts. If you were to kind of block your air-cooled condenser with a piece of cardboard or a panel, will it trip out at a certain point? And maybe you don't know what that point is for any kind of refrigerant, but if you take this principle, you can figure it out, and this is how I do it. So really the hottest temperature that you're going to see pretty much anywhere is 110 degrees outside. That's a good number. In fact, where I live, it just hit 111 the other day, which is the highest temperature I've ever seen here in Chatsworth. And if you add 110 plus 30, you get 140 degrees saturation temperature. And if you just look at 140 degrees Fahrenheit on a pressure temperature chart and then go across to the refrigerant that you're working with, you'll find a pressure. That pressure is a pretty good place to have your head pressure cut out. Just there would be an excellent place. So really here, if we look on a PT chart for 140 degrees, we see R22, 337 is a pretty good place for a head pressure cutout. R410A, 539. Now maybe a little lower because these newer high efficiency systems, maybe 525 or 530 would be okay. But the principle gets you there, close. R134A, 140 degrees on the PT chart, 229. So these are approximate places where the refrigerants should trip out on head pressure cutout, which is here. The symbol for a high pressure cutout is right here, opens on a rise in pressure, shutting off the circuit, protecting your compressor, okay? Now, let's talk a little bit about water-cooled condensers. Water-cooled condensers are more efficient. And then you may ask, well, why aren't they more common? Well, they're more expensive to install and maintain, but they probably use a little bit less energy overall. And they're very good in here in the Southwest where I live of the United States because we have typically dry summers. It doesn't rain much in Nevada, California, Oregon, Washington, western part of Idaho. Pretty dry summers. The rest of the United States, on the East Coast and the South, humid summers. But we use evaporation of water to provide cooling. So we have some different types of water-cooled condensers. We have a shell and tube condenser where the tubes run back and forth, and here you would have like 80-degree water coming in and 90-degree water coming out. We also have over here a shell and tube condenser where you have two tubes, water in the center surrounded by refrigerant traveling around picking up the heat, and this would be for a smaller type of water cooled condenser. The shell and tube condenser is really for large applications into the hundreds and even thousands of tons capacity. And we also have the shell and coil condenser. Now, how do we regulate head pressure on these? A lot of times we have a water regulating valve. And coming off of the discharge line, now this would be the discharge line for our shell and tube condenser, and coming out the bottom, like any condenser, you generally have, whether it's air-cooled or water-cooled, you have the discharge line at the top, and then the liquid falls to the bottom, and the liquid line comes out the bottom. You're tapping off the discharge line going to this water regulating valve. As the head pressure goes up, you increase the pressure on the water regulating valve. It opens up more, letting more water flow through, cooling off the condenser a little bit, and then the head pressure drops a little bit. If it drops too much, then the head pressure goes down, and it closes down. You let less water flow through, and the head pressure comes back up. So the water regulating valve is very simple, and it's always opening and closing just a little bit to maintain a pretty constant head pressure, and that's nice. That's how we maintain head pressure in water-cooled systems. Also, another point, if you're ever confused about water-cooled condensers, just know this, that I don't care whether it's shell and coil or tube and tube or shell and tube. Just remember this: on the outside of the condenser, on the metal where you touch, just below that is going to be, on the other side of that metal, refrigerant. And then traveling on the inner part of the condenser is the water. Just like over here, the water travels on the inside, surrounded by refrigerant. Now, why is that important? It's because here, if you see the refrigerant, it gives up heat to the water tubes inside, but it can also give off a little bit of heat to the ambient on the outside through the metal. So it's giving off heat in two directions. Where if it was the other way around and the refrigerant was on the inside and the water was on the outside, the refrigerant could only give up heat to the water and not to the surrounding ambient. So it makes it more efficient, and that's a good way for you to remember how does it actually function and look inside a water-cooled condenser. Now over here we have an evaporative condenser. An evaporative condenser, which is a lot like a cooling tower, but a little different. Not quite. And look for my video on cooling towers and chillers in your next assignment. Here is the discharge line coming, and so it would actually, be just like you have here, the discharge line. You could actually just draw this over there like that, and then the liquid line, you can draw that over there like that and get rid of this right here. And then the discharge line comes in here, and it travels through, and they actually have these handhole covers that you can open up and look in there at the condenser tubes themselves. And then you have this basin of water, and the water is filling up the bottom, and actually there's a float valve that brings in the water and maintains a certain constant level of water as water evaporates. And then you have a pump here that sucks the water off the bottom and brings it up to these spray heads that mists the condenser to get rid of the heat. And as the water flows over it, it cools off the condenser and lowers the head pressure. Now, it's also drawing air inside, and it really has something like this. It has, obviously, this isn't exposed to the atmosphere. You have something like this, where you have like louvers at the bottom that's going to allow air to be drawn in by the fans, and then as it passes over the water, some of that water evaporates and you see what's the proper term is a plume, that fog that comes off the top of your evaporative condenser, also appropriate term for cooling towers. And as the air travels in and goes over the condenser with the water falling, some of that water evaporates. And that's actually the evaporation of water, that latent heat process of water, is actually how we get rid of the majority of heat in evaporative condensers and in cooling towers. It's not just that the air may be cooler than the water, it's that some of that water evaporates and picks up the heat from the air and cools off the refrigerant. Here, now, we have up here what's known as eliminators, just like the ZZ Top album, and you might want to look up that video or images. It's pretty cool. Eliminators, and when the water gets too warm, here the fans come on and draw in more air through our louvers, and more water evaporates, causing the temperature to drop. So even for a cooling tower or an evaporative condenser, we maintain the water temperature with a thermostat that says, okay, you know, this is 80 degrees. When it gets to 81 degrees, bring on the fans. When the temperature drops to 76 degrees or whatever, 77, shut off the fans and just rely on the natural airflow going through the evaporative condenser or cooling tower. Some maintenance issues here is that you've got to keep these spray heads clean. Now, let me finish the presentation, just talk a little bit, I could go for an hour or more easy, on water treatment. With the evaporative condenser and also with cooling towers, you're getting water that's evaporating. And it's the pure water that evaporates and the minerals stay behind. Have you ever had a pot on a stove full of water and you boiled it and then life got busy and 3 or 4 days went by and you finally got some time off work and you look in the bottom of the pan that had been sitting there with a little bit of water in it and all the water has evaporated and there's a little bit of white powder at the bottom of the pan? You're like, how is this possible? Well, the water evaporated and the minerals that are coming in with the city water all the time, they don't fly up into the air. The rocks and the minerals and the calcium carbonate, they stay behind and they concentrate, okay? The same thing happens with a cooling tower and evaporative condenser is that when all this water evaporates, the minerals that were in the water coming in to the tower, which has minerals in it, from the city, the concentration of it goes up. The greater the concentration of minerals, the more likely those minerals are to stick to your condenser tubes, the warm condenser tubes, insulating them, which is called scale. And we don't want scale on our water-cooled condensers. So what we have to do, or actually let's look at this example here to help you understand. You see this pot of water with this little baby blue flame underneath it here, and I wrote 500. That might be a fairly high parts per million, but something that you might find where you live. 500 parts per million total dissolved solids. That means that there's, besides water, like calcium carbonate, minerals, salts, what have you, stuff in the water that isn't H2O, okay? And so if we have this fire on high and we boil off half the water, okay? We boil off half the water. Let's make it half exactly. The question is, what's the parts per million now in the water? Think. It's 1,000 parts per million because we have half as much water, but just as many minerals. You got rid of half the water and the mineral concentration doubled or went to 1,000 parts per million. Now, if we went over to the tap and filled it back up with tap water, think now, see if you can figure this out. What now is the parts per million in the pan? The answer is 750. Because remember, the water coming in from the city, right, was 500. So this was the 500 up here, and below here was 1,000, and equal parts, if you mix the 1,000 with the 500, you get 750 parts per million. And that talks a little bit about the idea of bleed off. The book says blow down. I used to run high pressure boilers. We use blow down for the boilers, but really bleed off is the better term for getting rid of some high mineral content water, dumping it down the drain, literally when the mineral content gets too high, and then when you bring in that fresh water, it mixes, lowering the mineral content, lowering the likelihood of the scale building up. So that we're not just having water going through the tower at one time, or water-cooled condenser, and that's it, dumping it down the drain. We recirculate that water and use it over and over, but the mineral content builds up, and then we have to get rid of some of that. That in conjunction with a scale inhibitor, which is a liquid polymer. It's like a slimy type of almost oily feeling thing that stays in the water that helps keep the minerals in suspense, or it makes the water just a little tiny weeny bit slimy and prevents the minerals from sticking to the condenser tube. So by getting rid of some of the high mineral content water and adding some scale inhibitor, we can save water and do some water treatment. There's a lot more to water treatment, like using algicides and working with conductivity controllers, but that's a story for another day. Also, please watch the video presentation I have for the class on chillers and cooling towers. Thank you.